Now that we have the definition of divergence, we're ready to present the divergence theorem. So here it is, theorem 8. Let F be a vector field whose components have continuous first partial derivatives. Everything's nice. Let S be a piecewise smooth oriented closed surface. The flux of F across S in the direction of the surface's outward normal field, N, equals a triple integral of the divergence, del dot F here, over the region D enclosed by S. So this is the flux over the surface, flux over the boundary surface. This is going to be the triple integral of the divergence here. But let me draw a picture. So, we just need some big 3D region here. And so S is the surface, and then D is the region inside of our surface. D is the filled in, S is the surface here. The double integral over S of F dot N, D sigma, the flux, this is flux over the boundary, is equal to the triple integral of the divergence of F over D. This is the integral, the triple integral of divergence over the interior. And this should feel very, 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 very similar. Here's our 2D version of Green's theorem, the flux divergence form. This is the flux. The flux over the boundary is equal to the double integral of divergence over the 2D region enclosed by this. This right here, this picture illustrates the divergence theorem. It's the very, very natural 3D analog of the flux divergence version of Green's theorem. Let me also just remind us here what the physical meaning of flux and divergence is and why this makes sense. Flux is the total flow of something through a surface. And the divergence is measuring how much stuff is moving outwards or inwards. Measures rate at which something is expanding or contracting. This makes sense. If you have something that is expanding, like a gas is expanding here, the divergence will be positive and stuff will be flowing through your boundary. So if we had some sphere here and we had a gas that's expanding, we do the the triple integral of the divergence of the vector field corresponding to expanding gas here. Well, that will give us something positive, and we'd be moving through the surface. The flux, there'd be outward flow here. That would also be something positive here. So we can see that, okay, it makes sense that these two quantities are related to each other, and then the divergence theorem shows us exactly how to precisely relate them together. And so in future videos, we'll do lots of examples of verifying the divergence theorem and applying the divergence theorem.